Generators are one of my favorite features in Python and a feature that I have thought very deeply about. I want to share with you a different perspective on generators, not too different, because for those of you who've joined our previous sessions on generators, you've heard some of this before, but a different perspective than one that you might already have. Here, we have a function and a generator, and they look very similar, except one has a return and the other one has a yield, and actually the generator can even have a return in it. And we can call the function, and it gives us some result. We can call the generator, and it gives it some result. But the result that the generator gives us is not the result of the computation. It's some entity that we then, in one level of indirection, call to then get the actual result. In other words, in the function, we run the function, and it gives us the data output that we want. It gives us our result. For the generator, we call the generator. It gives us this generator instance, and then we have to do something to that generator instance to go over to the actual output data. And it seems like there's an indirection here, but it's maybe not clear why this indirection is necessary or why this indirection is so fundamentally associated with what the generator really is. Well, here, if we take a look at the function and the generator, these entities themselves, not invoked, just themselves, they actually look almost identical. In fact, from the outside, from the pure Python level, it may be very difficult for us to determine whether something is a generator or a function unless we can either invoke it and see what it gives back, or if we can look at the source text, or if we can dig into the CPython level and see if certain flags are set. In truth, a Python generator is just a function that has a couple of flags set so that when you run that function, and it hits a yield point, it doesn't clean up the state for that function, the function frame. It just leaves the function frame around so you can resume it. A generator in Python is basically encoded as just a flag as a resumable function, just a flag on the function object so that when you create the frame, you can resume that function at any point where it stopped. Now, if we take a look at a function versus a generator, we might say, well, this is useful in part because in the case of a function, we have this very simple subroutine thinking. We put in some input and it gives us some output. We give in all of the input and it gives us all of the output. And there's no way for us to intermediate anything. There's no way for us to do anything in between the input and the output. It runs in one fell swoop. It runs eagerly. It gives us the result no matter how long it took for that result to be computed. It gives us that result, and we basically are sitting there waiting for that result after we give it the input. Whereas for the generator, typically the mode we have is it runs lazily, or in other words, we give it some input and it gives us some partial output, then a little bit more partial output, then a little bit more partial output. And in between those partial outputs, we can go and interleave some arbitrary behavior. We can get a partial output and then say, oh, I'm going to go off and do something else, and then come back and get another partial output and go off and do something else and then come back. And this is what we call lazy programming, or this is what we might call a lazy formulation, in that it doesn't eagerly go off and do the entire computation. It waits for you to say, give me a little bit more of the computation, a little bit more of the computation, a little bit more of the computation. Another perspective that we could look at if we were to consider generators is here, and this is one of my favorite ways to look at this. Here you have a string, and you have a Python list. And I like to ask people, what's the difference between the two of these? And I think a very superficial difference is one's a Python list and one's a Python string. And I'll tell you why I think it's a superficial difference. Because the underlying concrete data type, largely doesn't really matter that much. We can oftentimes, see things that might be encoded as lists, encoded as tuples, or encoded as sets, and there's certain behaviors associated with that. But it's a very superficial thing to say, oh, it's just a string versus a list. I'll tell you why I think this is a very interesting example, though. It's the same data. It's the same entities, A, B, and C. It's just that we've encoded them differently. In the first one, we've encoded these three entities, and we've delimited these entities using an in-band encoding. We've basically said there's entities A, B, and C, and in the same channel where we encode entities A, B, and C, we'll encode where A ends, where B ends, and where C ends using a comma. And there could be an ambiguity, because if there happened to be an entity in here that was called A, AA, it would be ambiguous. Wait, is that A, B, and C, or is that A, B, and C? Is it 3 entities or 4 entities? And we'd have to use some sort of quoting, or some sort of escaping, or we'd have to use some sort of entity that couldn't possibly be part of the data, maybe like a null character to, would use some sort of partitioning of the space. Whereas here, with the list, it's the same data, but we've used an out-of-band encoding. We've used the mechanics of the Python language to unambiguously indicate where one of these entities begins and ends, and we don't have any of that ambiguity. There is never a case where we're unsure where does one entity begin and where does the next entity end. It's very clear. Now, one of the things you might think is, well, x's is just the result of taking a, b, c, and splitting on a comma. So what's the real difference here? Understand that this is a decoding or a parsing operation, and that decoding or parsing operation is, number one, a heuristic, because, for example, how do you know that you're splitting on a comma and there aren't commas as part of the data? So you need to have, as part of that mechanism, whether there is quoting, whether there's escaping, whether there's partitioning. Additionally, this is an action that you're performing to transform the data from one encoding to another performance. So this is an encoding or decoding operation. It's a parsing operation. And what you're doing is you're using this parsing to take yourself from one unstructured or in-band encoding to a structured or out-of-band encoding. What you can think is, once we have this in this out-of-band encoding, in this structured formulation, we can do some very robust things with it. Namely, we can look at each individual item, and we can look at those individual items and delimit which item is which, and we can swap them out, and we can do some very careful surgical operations. Take the second item and look at it independent of the other items, take that second item and swap it out with another item. Well, if you think about it, this function does 3 computations. It takes W and adds 1 to it. It takes W and it doubles it. And it takes W and it cubes it. 3 operations. But we can't delimit these operations. They're done all at once. It's kind of like that string, which gave us the same data as the list, but didn't give us an ability, unless we had some mechanism by which the parser decoded, to split them up. Whereas what the generator gives us is the same computation, but split into 3 logical parts: the W plus 1, the W squared, and the W cubed. What you can think is that just as a list is a way for us to find an out-of-band encoding to structure data that might otherwise be encoded as a string, a generator is an out-of-band encoding to structure data that might otherwise be in some unstructured format as a function. But the data is not the typical data you think of. It's a computation. In other words, a generator is a way for us to take a big computation and to break it up into logical parts and to say, this is the first part of the computation, the second part of the computation, and the third part of the computation, and to give you a robust way in order to say, oh, just run the first 2 parts of the computation. Just run the first part of the computation. Don't run any parts of the computation. Unlike the list, which is random access, which allows you to access any of the elements, the generator is not random access. You can't arbitrarily say, oh, run the third computation, but not the first or the second. That's an important property of the generator, but you can at least delimit where one of those computation ends and begins. And you as a programmer decide what constitutes one piece of this computation, whether it is the computation of x and y together, or the computation of x by itself and then y by itself and z by itself. And this leads to how we might use generators. And so here you can see when we run f, it does all 3 of them, but when we run G, we can choose to run the ones that we want to run, or at least we can choose to run up to the one that we want to run. And if you've seen any of our previous presentations on generators, you may have even seen us dig around a little bit and look at the GI frame F last I. This is the last instruction that has been run in the generator. If you were to disassemble this generator and take a look at its bytecode, you would see that every time this generator yields, what's happening is the underlying function frame that runs this generator is just remembering, oh, what was the last instruction I ran? And it's leaving all of the state and all of the data around so that you can resume this just from this instruction. That's what GI frame left last I is. This is just the last instruction it ran. It's just a function that allows you to pause and resume it. Now, you have seen generators talked about in the context of performance. And I want to share with you that generators aren't really a performance mechanism, not in the way that we think. Because typically where we get performance is through eager computation with everything local in memory and everything, devirtualized. And so, for example, if we had some data set that's, a 10,000 by 10,000 matrix of values, 5 10,000 by 10,000 matrices, and we want to perform the sum of each of these, the generator versus the function, well, you know what? Doing this all eagerly on this data all at once in a function formulation is going to be faster than doing this on a generator. And so, if we run this, what we'll see from our timing is that G is going to be significantly faster. It'll always be the case that one of these is faster than the other. It's always the case that doing things eagerly is, oh crap, the function's actually slower. Well, one of the things you can see is as we change the shape of this data, the timings are going to change. Here, if we run this over, and let's actually remove this one. If we run this over 20 5,000 by 5,000 matrices, you're going to see that the eager function formulation is going to get a little bit faster. And if we run it over not 20, But 80 2,500 by 2,500 matrices, the function, the eager formulation, is going to start catching up. And if we take a couple of steps ahead and run it over 1,280 625 by 625 matrices, we're going to start to see that function formulation, that eager formulation, pulling ahead. And if we change this so that it's not 5 10,000 by 10,000 matrices, but 50,000 10 by 10 matrices, the function formulation, the eager formulation, will pull way ahead. Here's the story. The generator gives you the ability to break a computation into parts and to ask the question, do I keep going? Do you want the next part or not? That question and answer of, do I keep going? Do you want the next part or not? Happens at the pure Python level. If the amount of time that it takes to make a decision whether to keep going or not is larger than the amount of time to do the computation itself, then the generator may actually be a formulation that if the amount of time is significantly smaller, the amount of time to do the incremental computation, then the generator may actually be faster. If it's the case that the incremental computation is faster than the time it takes to make a decision, then the eager formulation is likely to be faster. And here, this is what you can see in the dynamic here. If I have 50,000 matrices, but they're 10 by 10, that 10 by 10 sum is really fast. And so going into the Python level to see, do I keep going or not, is actually slower than just going all the way ahead. Whereas if it's 5 10,000 by 10,000 matrices, one call to the Python level to say, do I do this 10,000 by 10,000 sum? That's actually going to be faster than deciding whether you continue or not. And so even though generators are oftentimes presented as a formulation for increasing performance, it really isn't quite about performance in that way. It really is about identifying the incremental computation that I want to perform and the decision whether to keep going or not. Which of these is more expensive? If the decision to keep going is more expensive than the incremental computation, do it all eagerly, just pre-compute everything, throw away the results you don't need. If the decision to keep going is faster than the incremental computation, then do it lazily, because then you'll be able to say, do I keep going, do I keep going, do I keep going, and you won't waste time doing computations you don't need. Why does this matter? Well, fundamentally, Python doesn't really give you control over memory usage. It actually gives you better control over CPU usage over time, and the generator, as a consequence of giving you a little bit more time control and a little bit more memory control, subject to the previous qualifications that I added, gives you the ability to add a certain type of useful program structuring, not only sequencing, but a higher level program structuring. Let's take a look. In Python, you may have noticed that you can't really control how big anything is. You can't really control where things are laid out. From the pure Python level, you can see this name tuple with 3 8-byte integers is 64 bytes in size. Well, 3 times 8, that's 24. The data itself is only 24 bytes. I am wasting 40 bytes of overhead, more overhead than the data itself to store this name tuple. And Python gives you no ability to really control this. It gives you a little bit in the form of things like slots, but for the most part, you can't say, Python, pack these really close. Python, don't have some pointer level indirection here. Python, make this an unboxed object. Everything is boxed in Python. Beyond this, you can't really control allocation or deallocation in Python. You can't really tell Python, oh, perform an allocation here, perform a deallocation here. However, in Python, you can actually control CPU usage, and we have a very common way to control CPU usage. Namely, if you have some operation that you're doing at the pure Python level and it's too slow, you drop down to the C level, write a C extension module, and you get a faster formulation for it. You use Cython if you want to bridge that divide between Python and the C level or the C++ level, or you use one of the other tools, PyBind11, there's a bunch of these. And so we see this as a very common pattern. Instead of doing something slowly at the pure Python level, we might do something faster at the C level, and Python says, I'm completely okay with you dropping down to the C level. Python actually gives you the ability to really closely control how much time you're spending on operation by determining when you want to drop down to C versus when you want to stay in pure Python. But it doesn't really give you the ability to control how much memory is being used. There's a lot of stuff behind the scenes in the Python interpreter. There's free lists and arenas that don't necessarily get deallocated in the way that you might think. And so you never really can say, oh, Python, stop using this memory over here, stay within this memory budget. Now, We do have workarounds, and they're not too dissimilar from this. For example, if we wanted to control our memory use, we might use something like NumPy, and this is basically using NumPy as a safety valve or as an escape hatch. Just escape the constraints of pure Python, intermediate the data entirely, pull everything to the restricted computation domain, and Python doesn't really know that the data is there. It really only knows that this manager class is here. And that's not too dissimilar from our approach, at least in terms of controlling performance from a time perspective, but you can see Python really doesn't give you the ability to force allocation or deallocation. Simply, you cannot force Python to deallocate memory. Dead stop. You don't know where references are stored. You don't know what might be holding onto a reference somewhere in Python. You don't know if the underlying memory for something that you've cleared all the references for will actually call a free as opposed to just leave it in a free list or some cache or some buffer. You cannot force a deallocation of Python. Del only decrements a reference count. It does not force the destruction of an object or the deallocation of an object. And you can't even force an allocation. And you could say, well, sort of you can, because you can write a list with literal values and that force an allocation. Not really, because if that object that you're creating is immutable, you don't know for certain that Python did an allocation to create that object. It could have returned to you something that was interned, like small strings and small integers. If it was a mutable object, you don't know that Python actually did the allocation. Maybe Python gave you something as an intermediary, like a pandas range index, that doesn't really represent the allocated data, but represents something between you and the allocated data. So you can't really force allocation or deallocation of Python. You do not have fine-grained control over memory use, in the same way that you might have fine-grained control over CPU use. So what you can think is that generators are an API structuring mechanism that allow you to try to retain a little bit of that control. In other words, with the generator, you can say when the computation begins and when the computation ends. You can say use this much computational time by just not doing extra work. And if you look at that crossover mark between the time that it takes to make the decision to keep going and the time that it makes to do the incremental decision, you can find that sweet spot and say, after this sweet spot, it's worth me asking every step along the way, do I keep going, do I stop, do I keep going, do I stop, and I can control the total amount of time. Additionally, if the operation you're performing is done on a data set and you do not need the entirety of the data set all at once to perform that operation, for example, instead of performing, say, a determinant of a matrix where you need the entire matrix, you're doing a row by row or column by column operation. You can control memory by just not bringing into existence the memory that you're not looking at any point in time, and then crossing your fingers and hoping that the standard Python deallocation cleans things up for you. You still can't really control that, but with the NumPy and darray, there's only so many places references can hide. There's only so much that can really happen. And so even though you can't strictly control that deallocation, you can at least generally control it and generally have some sense of, I only need one row at a time, allocate for that row, and then throw it away, allocate for that row. When I say generators are an API structuring mechanism, I mean this absent any notion of performance. Because imagine you have some simulation, and that simulation cannot be performed eagerly within the NumPy restricted computation domain or a pandas restricted computation domain. It's necessarily something iterative. It's necessarily something that you need to add custom code at the pure Python level in order to implement. How do simulations start and stop? Well, some people want to start their simulations, or stop their simulations rather, after a fixed number of steps. Some people want to stop their simulations after the simulations hit a certain benchmark, a certain threshold. Some people want to stop their simulations after their simulations run for a set amount of time. And each of these modalities for controlling the endpoint of the simulation would need to be encoded in the actual function if this were written as an eager function. I'd have to say simulation, max steps equals something, or max time equals something, or max value equals something here. And I'd have to internalize that control over the simulation. Functions as an eager processing mechanism force you to control in an internal fashion how much computation is done if it's not the case that the computation is always done in some set amount. In the case of a simulation, you can think, well, a simulation is multiple steps for the simulation. So sometimes you want to do some of that simulation, sometimes you want to keep going, sometimes you want to stop. The generators externalize your ability to control this via other generators that you write, like my time generator here, or via things like the itertools module, fundamentally what it's about is taking the API for controlling when something starts and stops and making that something that is not built into the entity itself. Because you can think, it's not one simulation you have, it's 50 simulations. Do you really want to have a max steps, max time, max value argument for all of them and all the corresponding unit tests for that? And hold on a second, those are just 3 modalities. Somebody else comes and says, you know what? Run the simulation until adjacent return values for this simulation are no longer 1% better. The next value is no longer 1% better than the previous value. That's another modality. And that adds complexity to everything you have to do. Whereas if you had implemented this as generator, you could easily encode that as just some take while using an nwise, nwise the simulation results to get the previous and the current, and then do a take while to see, okay, as long as the previous and the current are within some particular range of each other. This is what generators are all about. It's about structuring your code differently, where that code can be broken down into steps, and you want to control how many steps do I do, when does a simulation start and stop. Additionally, in a narrower case, we can think of this as a sequencing mechanism. In other words, let's say we have 3 functions, f0, f1, and f2, and we want to force these functions to be called in a particular order, f0, then f1, then f2. We could wrap this in another function, but because this function here is eager, we can't interleave behavior arbitrarily. We could interleave behavior up here, but if we wanted to interleave different behavior, sometimes we want to do something here, sometimes we don't want to do it, sometimes we do a different action, we'd have to add modalities. And that's going to make this more and more complicated. Whereas, if we were to encode this as a generator, what we could do instead of running f0, f1, and f2 manually, which could then be run out of order, we could create a generator and run through these steps, G1, by calling next on this generator, force that f0, f1, and f2 run in exactly and nothing but that order while still preserving the ability to interleave any arbitrary behavior at call site in between. And the only thing that we lose from this is we can't ensure that all of these steps occur. This is why when I write my context manager, I rarely write it using a class. I usually write it with a generator. Because you can think a generator is a sequencing mechanism. The before and the after parts of the context manager are just what I do before I yield and what I do after I yield. The thing that happens inside the context manager is what I do when I yield, and I use this decorator here in order to get everything to comport with the Python object model as our means of how we implement this vocabulary. Now, as we said before, let's think about how many lines of code it would take before a generator comes up. I think a generator could easily come up in a 10-line script or a 20-line script. Anytime you want to take a computation and you want to say, I'm going to logically break it down into steps that make sense to a human being, step 1, step 2, step 3, and externally control how I proceed through those steps, arbitrarily interleaving things in between those steps, a generator comes up. It's one of the tools that you will use even in very, very small scripts.